Really, there's nothing is off the table, okay, as far as the types of equations you can see now, or types of functions. How about this one? F of x equals 2 cosine x and then plus sine squared x. And let's look on the interval 0 to 4 pi. You all took pre-cal, right? I always tell my pre-cal classes that there are two major outcomes that you want from pre-cal. One is you want to understand the unit circle. You want to understand how it's connected to all your trig functions. First. Second, you want to be able to solve trigonometric equations, which is what this is going to turn out to be. All right, so we're going to test that, your knowledge here, and I know there will be gaps, so I'll go through it thoroughly, but just understand that, that could appear on the homework, on test. This is fair game. All right, so let's follow the process. Is this a continuous function on a closed interval? Cosine is continuous, right? Sine squared is continuous because sine is continuous. If you square it, it's still continuous. And when you put these two continuous functions together, it's continuous. So this behaves well. No division by zero, no roots of negative numbers, right? Nothing bad happening. So if it's continuous everywhere, then it's definitely continuous here. And do you want to look at it first, or you want to just go with do the math? Do the math? Okay. Derivative, right? All right. What is the derivative of this function? Negative 2 sine x plus, now how you can take derivative of sine squared x? Yeah, it's like sine x all squared.
2 sine x, then the derivative on this side.
2 will drop out, sine x, and then times cosine x. So everyone, that's what sine squared x meant. So you drop the 2 out. 2 sine x, then derivative of the inside is cosine. So we got that. We all good? Set that equal to 0. So you set negative 2 sine x plus 2 sine x cosine x equal to 0. This is what we refer to in pre-cal as a trigonometric equation. So how are you going to solve that? Everyone see 2 sine x, common factor? Okay, factor it out. I can go 2 sine x or negative 2 sine x, doesn't matter. I'm going to go 2 sine x. Tell me what I would have left in here. Negative 1. I pulled a 2. If you pull a negative 2, then it would be 1. I'm pulling a 2, so I get negative 1 plus cosine x equals 0. Set each of them equal to 0. So I have over here 2 sine x is 0, and the other one is negative 1 plus cosine x equals 0. Right? Two different equations I have to solve. And the first one I can just divide by 2, and this is just saying sine x is 0, right? And this one over here, I can just move the negative 1 to the other side, and this is saying cosine of x is 1. And these are two separate things, right, that I have to deal with. These are two separate ideas. So what?
What is the y value? 0 will be at pi. Yeah, pi.
All right. this is a little asterisk, which means this is important because you need to understand, you need to have a way of doing this, all right? I'm going to try and not reteach it, but I'm going to just try and make sure you know how to do this. Where is the sine function equal to 0 is the question, right? When is sine 0? Now, if I say just look between 0 and 4 pi, you could do this. Now, don't do this, but watch. You could just say, hey, here's sine, right? I know sine looks like this. That's 0 to 2 pi, right? And then I can do another period, and that's 0 to 4 pi. And I can say, okay, where is it 0? Here, 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 and here. So what are my answers? This is 2 pi right here. So I could get what? 0, pi, 2 pi, 3 pi, and 4 pi, right? That would be 5 answers. I would have 5 critical numbers from this. Agreed? And then for cosine is 1, I can do the same thing and draw a cosine. And that's all great, but you need to be able to solve and get the general solutions. So I'm going to show you how to do that. And it's much more useful for you, moving on in math, to be able to do what I'm about to show you. We will still get these answers, but we'll do it in a way that's more powerful. So when I look at this problem, what I say to myself is, on the unit circle, sine is actually corresponding with which coordinate on the unit circle, the x or the y? The y coordinate. So what we want to know really is, when is the y coordinate on the unit circle 0? And that happens here and here, right? Now those angles, if you look at them, are the angles 0 and 180, which is pi, right? So I have 0, I have pi, but I could swing through again all the way to here and stop, and I'd be at 2 pi. Then I could swing around again, I'd be at 3 pi, and then come back around, and I'd be at 4 pi. And then I could go 5 pi, and 6 pi, and 7 pi, and 8 pi, and 9 pi, right? If I'm looking for general solutions, forget this. That's what that picture represents. So I need a way of writing that down. Okay? The angle, this is the angle, x, must be equal to this angle, 0. And then how much does it take for me to swing over to the other angle? I have to add pi to it. But I could have added, instead of 0 and adding pi, I could have added, what, 2 pi, and that would have brought me to here? So we use this notation n pi, or pi times n. Do you remember seeing that in pre-cal?
I remember seeing K.
You could use k also, yes. That's right, it's k. This book, the books I'll use here use k. K or n, doesn't matter. So the way we do it in pre-cal is we say, okay, give me a starting place, that first red dot. That's the angle 0. And then to get around from this point to that one, I'm just going to add 1 rotation of pi, 1/2 rotation, which would be pi. And then to move back to this one, another pi, and then back there, another pi. So this k here represents how many multiples of pi I'm going to use. So k comes from the set. K can be any integer. So any integer. If you plug any number in here, any nice integer, 9, -10, if I plug that in here, I should land on one of those red dots. Make sense? Now let's figure out which of these answers, which I could also rewrite this because 0 doesn't matter, does it? 0 plus pi k is still pi k. Now I figure out which of these answers, because this is an infinite number of answers, which of those live there? So I start with k being 0. If k is 0, what's my answer? 0. So one answer here. If k is 0, we get x is 0. What if k is 1? X is pi. What if k is 2? 2 pi, and then 3, 4, 5, so you get 3 pi, 4 pi, and then once I get to 5 pi, what? I throw it out, right? I throw it out because it's outside my interval. Got it? All right, let's come over here. Cosine of x equals 1. Unit circle again. Cosine is which coordinate? It's the x coordinate. Where's the x coordinate 1? Just here, right? Just there. So you write instead x is equal to 0 plus, now to get from here back to here, you can't do half rotations. You have to do full rotations. Full rotation is 2 pi. So you go 2 pi k. So x is 2 pi k. Got it? So if k is 0, you get 0. If k is 1, you get 2 pi. If k is 2, you get 4 pi, and so on and so forth. But we notice that every answer here is actually already included over here, isn't it? So these are my only critical numbers. Understand? All right. What about, we've done the derivative of 0. Where's the derivative not exist? Or does that happen? Here's my derivative, right? You're going to run into any problems there? Division by 0, square roots of negatives? No? So the part where we have f prime does not exist for us does not apply here. So I think I'm ready. I'm going to plug into my function the endpoints and then all my critical numbers, which there were 5 of them, weren't they? Weren't there 5? No, yeah, 5 of them. But 2 of them were the endpoints, weren't they? Like 0 and 4 pi happen to be our endpoints. So really I only have 3 different values to plug in. Pi, 2 pi, and 3 pi. You happy? Yep. Okay, plug them in, see what happens. This should be pretty straightforward. 0, cosine of 0. And remember, we're not plugging into the derivative, right? Into the original. Cosine of 0 is 1. 1 times 2, 2. Plus sine of 0, 0. So this is just 2. All right, 4 pi. What's cosine of 4 pi? 1 again, times 2, so 2 plus sine of 4 pi, 0 again, squared, 0? I mean, yeah, 0 squared, and then that's 2. All right, what about pi? What's cosine of pi? -1, so -2. What's sine of pi? 0, so -2. 2 pi? Cosine of 2 pi? 1, so 2. And then sine of 2 pi, 0. This, we're getting 2 a lot, aren't we? And then 3 pi. -2 again. What's the global maximum? 2, global minimum, -2. The global maximum occurs in 3 places. The global minimum occurs twice. Yeah? Let's take a look. What was it? 2 cosine x plus sine x squared. And we want to go from 0 to, I don't know if I can type in 4 pi. Let's see what happens. No, that didn't take that. Maybe I need to put 4 times pi. Oh, you know what my problem is here? Can you all see it?
It's like it flattens out.
Does look like it, right? But we have our global maximum occurring at 0 and at what, 2 pi? And over here at 4 pi, right? 0, 4 pi, and 2 pi are where our maximums occurred, and our minimums occurred here at pi and 3 pi. Get it? All right. You all look thrilled. Last one, we'll call it a day, all right? It's really critical that you do all the homework. I have worked out all the odd problems, like out of your homework set, I've worked out all the odd problems, and I've been doing some of the even ones on the board today. So between what I've done on my homework solutions and what I've done in class, you've got a pretty good mixture of everything that I'm throwing at you. But there's a lot of algebra in here. I don't have enough time to go through each problem. Each problem presents its own algebra. And so it's important that you go through these. All right? Don't just be like, yeah, I totally understood what he was doing. I just take derivative, set it equal to 0, see where it's undefined, I'm done. I know what I'm doing. Like, you have to get in there and see what kind of messy stuff happens. Let's try this one. It doesn't look too bad. I'm trying to pick between these two. Let's go with this one. This one looks worse. X minus 2 arctangent of x, and we're looking on the interval 0, 4. Is this a continuous function on a closed interval? Uh-oh. Do we know what arctangent looks like if we were asked to graph it? Okay, so this is what tangent looks like. That's tangent, right? That's tan x. And it continues, it repeats itself. It's periodic. But to define the inverse tangent, what we do is we cut off tangent and we just look between, do you remember what we look between? Negative pi over 2 and pi over 2. Good. That's what tangent looks like. Its inverse function, which is what we have up here, is, see if you go back to college algebra, all inverse functions are reflections over the identity. So imagine taking this black function and reflecting it over the red, and you would have this. Like that. Does this ring a bell? If you have a function and its inverse, that the domains and ranges switch places. So the domain of a function f becomes the range of its inverse, and the range of a function f becomes the domain of its inverse. In other words, this is pi over 2 up here, and that's negative pi over 2 down here. And let me take out tangent. That's arctangent right there. Okay, there's arctangent. That's arctangent. Got it? So, what is the domain of this arctangent function? Is there anything you cannot plug in? No, it's all real numbers. You're good to go. So this is continuous everywhere. That's continuous. We're good. But it's worth investigating. We can't just assume it, all right? Now, derivative time. Derivative is not so bad. Derivative is just what? 1 minus 2. And then we spent a day on derivatives of inverse trig functions, right? And this was one of the ones I said was really important. It's 1 over 1 plus x squared. There's your derivative. And if I just rewrite it I could put 1 minus 2 over 1 plus x squared. Everyone agree that's my derivative? It actually doesn't look too bad, does it? This problem may not be as hard as I thought it was going to be. We have to set that equal to 0, don't we? Yeah, let's see. If I need to set that to 0, yeah, I'm going to want to do that thing where I only look at the numerator. But that means I need a common denominator here. So can I put those two together? Is that all right? Make that a 1. So what do you have to multiply top and bottom over here by? 1 plus x squared. So it becomes 1 plus x squared. I'll do a little detail here. 1 plus x squared again, minus 2 over 1 plus x squared. So I'm just rewriting the 1 as 1 plus x squared over 1 plus x squared. And then that becomes my final version, which is what? 1 plus x squared minus 2 is on top, right? 1 plus x squared minus 2 is on top, and on the bottom, 1 plus x squared. What's the top? You could do negative 1 plus x squared or x squared minus 1. And on the bottom, I could rewrite that as x squared plus 1. Do those x squareds cancel? No. That is a difference of squares. So I'm happy with this answer, right? I'm going to leave it like that. That's my derivative. Okay? That's it. Now, when is that 0? So a fraction can only be 0 if the top is 0. And that I can get two ways. I can do difference of squares here, write it as x plus 1 times x minus 1. Or I can move the 1 to the other side and take the square root. When I do that, I have to do plus or minus. So either way, you need to make sure you can get two answers here. What about the derivative not existing? What do y'all think? Here's my derivative right here. Yeah, the derivative, not the original one. How about here? Should be good to go, right? The only thing that could possibly happen is division by 0, right? Like that's what I'm maybe concerned about because I have a fraction. But this can never be 0, right? X squared plus 1 cannot be 0, at least if we're not allowed to plug in real numbers, right? I mean, sorry. At least if we are restricted to the real numbers, then there's no solution, no real solution to that. Everyone agree? Yep. So I'm good to go. I have my critical numbers. Were both of these in the interval? I almost forgot to check that. Not negative 1. I can chunk negative 1. Only because of this interval, right? That's the only reason I'm chunking it. So now I plug in to the original function, f of 0, f of 4, and f of 1. It's not so bad. If you plug 0 in, 0 goes right here, that's 0. What's arctangent of 0? That you can use your calculator for. Make sure you're in radian mode, not in degree mode. You should get 0. So if you plug in 0, you get 0. How about 4? You're going to get 4 minus 2 times, I need someone on their calculator to put in arctan of 4, because that's not a common 1.325 something? Yeah. All right. And what is that if you work that out? 1.34, is that what you said? 1.3. 1.34, approximately, right? I mean, we could say squiggly equals approximately. 1.35. You round it? Okay. Close enough. All right, what about 1? You should get 1 minus 2 times an arctan of 1. 0.79? And then go ahead and do that for me. Should be a negative number. Negative what? Negative 1.21. Okay, sounds fair. That's it. You see? You disagree? 0.57? Yeah, that seems right. That we have agreement on that? So we have our max, right? Max is here. Minimum's here. Global. Do we care to graph it? No? Okay. All right, well, that's it for today. So here's what we're going to do. I think I'm going to skip 4.2 and do it at the end. Remember, I don't know if I told you, 4.2 can float. I think we'll get through this section and then push 4.2 to the end. So I plan on starting 4.3 next time. And 4.3 is where, and I think you could kind of tell with what we did today, especially on that one problem that went like this, right? That one. Like this wound up not being part of our answer, but there was something happening there. We had a local maximum here. And that's what the next section is about. 4.3, it's derivatives. It's called, the name of the section is derivatives and the shapes of graphs. Somehow the derivative is going to help us determine what the shape of a graph of a function looks like. And we're leading into being able to graph a function by hand completely. And then word problems. Happy Halloween. Everybody have fun tonight. Or even if you're not doing anything, still have fun.